Welcome to The Explainer. Today, we're going to tackle a foundational concept in mathematics, one that actually describes how pretty much everything changes. We're talking about differentiation. Okay, so let's just dive right in with a question that sounds super simple but is surprisingly tricky to get your head around. If you're driving a car, how fast are you going? Not over the last minute, but right now, at this single fleeting moment.
And this brings us to what's often called the speedometer problem. It really gets to the heart of the difference between measuring something over a stretch of time versus measuring it in one specific instant.
Look, we all get average speed, right? If you drive 120 kilometers in 2 hours, your average is 60 kilometers per hour. Easy. But that number you see when you glance at your speedometer, your speed right this second, that's instantaneous speed. And figuring that out, well, that takes a much cleverer approach.
So how do we do it? Well, the solution is actually beautiful. Let's switch to a visual, because geometry gives us a brilliant way to sneak up on the answer. Okay, imagine your car's journey is plotted on a graph. Time is along the bottom, distance is up the side. Now, if we pick any 2 points on that journey and draw a straight line connecting them, that's called a secant line. The steepness of that line, its slope, is just the average speed between those 2 moments.
But here's the thing. We don't want the average speed. We want the speed at one instant. So what happens if we start to slide those 2 points along the curve, bringing them closer and closer and even closer together? We're shrinking that little window of time.
As that distance between the points gets ridiculously infinitely small, watch what happens. That secant line pivots until it just kisses the curve at one single point. This new line has a special name. It's called the tangent line. And its slope? That's the speed at that one single instant.
And boom, that's it. That's the big idea. This thing we just found, the slope of the tangent line, is the derivative. It's just the official mathematical name for the rate of change at one single instantaneous moment.
So having that visual in our heads is awesome, right? But now we need to see how mathematicians take that beautiful geometric idea and write it down using the precise language of math.
All right, now, don't let this equation scare you. I know it looks a little intimidating, but trust me, it's just a recipe for exactly what we just watched. It's the instruction manual for turning a secant line into a tangent line, just written down in symbols.
Let's just break it down. The top part of that fraction, that f of x plus h minus f of x, is just a fancy way of saying how much distance did we cover. It's the rise on our graph, the vertical change between our 2 points.
And that little h on the bottom, that's the run, the amount of time that passed between the points. So we've got rise over run, which is just the slope of our secant line. The real magic is that limb part out front. That's the mathematical command that says, okay, now do what we did visually. Squeeze h all the way down towards 0.
So we have the concept, we have the formula, but what's the point? I mean, why is it such a big deal to be able to measure the rate of change at a single instant?
Well, it turns out this idea is used everywhere. In physics, it's the language of motion. It's how you define velocity and acceleration. In economics, it lets you find the marginal cost of making just one more widget so you can maximize profit. Engineers use it to find the perfect shape to make a beam as strong as possible. And get this, it is the absolute engine behind modern artificial intelligence, helping models learn by constantly minimizing their errors.
And here's the incredibly powerful shortcut this gives us. Think about the very top of a hill or the very bottom of a valley. For that one brief moment, the ground is perfectly flat, right? The slope is 0. The change has stopped. That means if you want to find a maximum, like maximum profit, or a minimum, like minimum cost, you just have to find the exact spot where the derivative is 0. It's an amazing trick.
So let's just quickly recap the journey we've been on to wrap our heads around this incredible idea. We kicked things off with a simple question about a car. Then we found a really elegant visual answer using geometry, turning a secant line into a tangent line. After that, we captured that whole process with a formal definition using limits. And finally, we saw how that one single idea unlocks the power to analyze and optimize pretty much everything around us. And that really brings us to the core of it. Differentiation gives us this incredible tool for understanding a world that is in constant motion, constant flux, which leaves us with a final thought to chew on. What are all the other hidden rates of change in technology, in the economy, maybe even in your own life, that are shaping your world at this very instant?